Today, we're diving into a landmark paper that really truly changed the game for how artificial intelligence sees the world. So, for years, you had this incredible AI architecture, the Transformer, that was just crushing it in the world of language. I mean, it was powering everything. The biggest question floating around the AI community was simple. Could this thing, this genius at language, be taught how to see? To really get why this was such a breakthrough, you got to understand what the world of AI looked like right before it happened. There was this very clear line in the sand. On one side, for anything to do with vision, like spotting objects in pictures, the heavyweight champion was the convolutional neural network, or CNN. But on the other side, for language, the new king was the transformer. They basically lived in two different kingdoms, each ruling its own domain. One was the master of pixels, the other, the master of words. So what do you think happened when researchers tried to take the all-powerful transformer and just drop it into the world of images? Well, let's just say it ran into some serious problems. The first big attempt to do this was called the Vision Transformer, or VIT. And, it was a brilliant idea, a fantastic proof of concept. But it immediately exposed two massive challenges in getting a language model to understand visuals. Okay, problem number one was all about scale. See, in language, words are pretty neat, tidy units. But in a photo, an object like a cat can be a tiny little speck, or it can take up the entire frame. VIT tried to handle this by just chopping the image into a grid of same-size squares. It was kind of clumsy. It just wasn't flexible enough to deal with how much objects can vary in size. But the second problem? Oh, this was the real killer. A transformer's superpower is that it looks at how every single piece of data relates to every other piece of data. That's fine for text. But for a high-res image with millions of pixels, the number of calculations just explodes. It's called quadratic complexity. Think of it like this. In a room with 2 people, there's one conversation. With 10 people, there are 45. Now imagine that with millions of pixels. The computational cost was astronomical. It was basically impossible to process large images. Now you can actually see the solution right here on this slide, which is what makes it so cool. On the right, you've got that rigid single-scale grid from the old VIT model. It looks at the whole image at just one resolution. But look at the left. That's the Swin Transformer. It builds up its understanding in layers, like a pyramid. It starts small, then merges things together to see the bigger picture. It's much more like how our own eyes work, right? So how on earth did they do it? How did they get that clever pyramid structure? It all came down to two beautifully simple but incredibly powerful ideas. The researchers called this the shifted windowing scheme. So first, to solve that crazy computation problem, the Swin Transformer doesn't try to look at the whole picture at once. Instead, it only calculates all those relationships inside small, local windows. This one change makes it incredibly efficient and breaks that curse of quadratic complexity. But you might be asking, well, if you only look inside those little boxes, how do you ever see the whole picture? And this right here is the brilliant part. In the very next layer of the network, the model just shifts the grid. The new windows now cross over the boundaries of the old ones, which lets information flow between them, connecting the entire image. So this is the absolute key takeaway. The shifted window idea gives you the best of both worlds. You get the local efficiency you need to handle huge images without your computer melting, and you get the cross-window connections to build a real global understanding. It was this elegant trick that finally unlocked the transformer for high-resolution vision. And the results? They weren't just good. They were absolutely revolutionary. The Swin Transformer didn't just compete with the old CNNs, it just blew them out of the water, across the board. Let's start with object detection, the task of drawing boxes around things. On the main COCO benchmark, it beat the previous state-of-the-art by 2.7 points. Now that number might not sound huge, but in this field, that is a massive, massive leap. Okay, how about semantic segmentation? That's where you have to understand what every single pixel in an image is. It set a new record there, too, on the ADE20K benchmark, improving by a whopping 3.2 points. And of course, on the classic ImageNet test for just identifying what's in an image, it achieved a stellar 87.3% accuracy, proving it could handle the most fundamental vision task with no problem at all. So when you pull back and look at the whole picture, it's crystal clear. Across these 3 core computer vision tasks, Swin Transformer just became the new state of the art. It wasn't just a slightly better model. It became a true general-purpose vision backbone that everyone could build on top of, just like CNNs were for years. But the impact of this work goes way beyond just setting new records on a leaderboard. It really points toward a brand new future for artificial intelligence. The authors themselves put it perfectly in their paper. By creating a transformer that could see just as well as its cousins could read, they kicked open the door to a unified architecture, an AI where knowledge from images and knowledge from text could be shared and learned together. You see, this breakthrough was never just about teaching an AI to see better. It was about creating a common language for intelligence, finally bridging that gap between sight and thought. And it leaves all of us with this really incredible question. What becomes possible when an AI can finally see and read with the same unified mind?